Did you know that NileRed and NileBlue YouTube channels are actually named after a chemical compound? Yep, if you Google it, you'll see. Oh, it looks like NileRed is so popular now that the Wikipedia page is not important anymore. But if I go a bit further, here it is. This is NileRed, the real one. It's phenoxazine dye frequently used in biology to stain lipids. And this is NileBlue. As you can see, the only difference between those two is that the amino group in NileBlue is hydrolyzed to ketone in NileRed. So theoretically, if I make NileBlue, I can easily turn it into NileRed. When I scroll a bit down, we can see that NileBlue is prepared by the condensation reaction of 1-amino-naphthalene and this compound called 5-diethylamino 2-nitroso phenol. It might seem overwhelming at first, but if we recall that both the hydroxy and the diethylamino are ortho and para-directing groups, we see that the preferred position for electrophilic aromatic substitution is on those three places. However, the diethylamino group is quite bulky, so practically we will get only the 2 derivative. And about the 1-amino-naphthalene, it can be directly bought from a local supplier. To make the plans real, I purchased 3-diethylamino-phenol from Sigma, and now it's time for nitrosation. This compound came as black plates, and I'm not really sure that this is its natural color. It probably has gone through a bit of oxidation from air. Despite that, I decided it would be sufficiently pure for the reaction to work and proceeded without purification. I measured out 10 grams of it in a 250 ml Erlenmeyer flask. I then put the flask on my hot plate and added a Teflon stirring bar. I also measured 22 ml of concentrated hydrochloric acid and diluted it with about 10 ml of distilled water. For the reaction, we need the hydrochloride of 3-diethylamino-phenol, so to get it, I added the hydrochloric acid to the flask. This generated some steam, which is pretty typical when amine is being neutralized with hydrochloric acid. I need one more reagent to carry out the reaction, and this is sodium nitrite. 4.17 grams of it were measured in a beaker and then dissolved in 30 ml of water. If you have followed the stoichiometry of the reaction so far, you will notice that the hydrochloric acid I added was in excess. This is because we need some of it to not only turn the 3-diethylamino-phenol to its hydrochloride, but also to convert the sodium nitrite to nitrous acid, which will be the active ingredient. However, nitrous acid is very unstable at room temperature, so I had to cool the flask in an ice bath. After that, I placed the nitrite solution in an addition funnel and equipped the flask with a thermometer to monitor the temperature of the solution during the reaction. When the temperature dropped below 5 degrees Celsius, I rotated the stopcock and started to add the solution dropwise. At first, no reaction seemed to occur. However, very soon the temperature rose to 4 degrees Celsius, indicating that reaction was happening. What is going on is that the hydrochloric acid converts the nitrite to nitrous acid. This nitrous acid is then protonated and liberates water, forming a nitrosonium ion. This nitrosonium ion is an electrophile which would attack the activated aromatic ring, forming a complex. Finally, this complex liberates a proton, forming our reaction product. Very soon, a brown precipitate started to form in the flask, which should be the nitrosated product. The whole addition took about 2 hours, during which the color of the reaction mixture became brighter and in the end nearly yellow. It was all filled with this fine yellow precipitate, which made the mixture very thick and hard to transfer. Nevertheless, I poured as much as I could in my Buchner funnel and washed the rest with a bit of distilled water. Keep in mind that although it appears as a precipitate here, this stuff is very soluble in water and can be easily dissolved if you use more water. The only reason it is not fully dissolved in my case is because it is in very concentrated solution with only a few milliliters of water present, which are not enough to dissolve it. Another interesting thing is that even though it appears as a yellow cake, it colors the solutions red, as you can see it here. This reminds me of the solvatochromic properties that NileBlue has, but we are still very far away from there, so for now let's just keep going. Filtering and fully drying it on the pump turned out to be a very difficult task because of the fine precipitate. I ended up breaking it with a spatula and transferring it to a drying dish. Then I set my hot plate to 45 degrees and left it to dry overnight. Keep in mind that the nitroso compounds are usually not very stable, so cranking the heat too much will decompose the product. Even the next day it wasn't fully dried, so I transferred it to a beaker and kept it warm for a little longer. Now it's finally dry, but it is all in large lumps, which is generally a bad thing if you plan to do reactions with it. To solve the problem, I took a glass topper and crushed it into smaller pieces. It took me some time, but the results were definitely worth it. Now it's time to make the NileBlue itself, and for that I took 250 ml flask and measured 2.36 grams of the 5-diethylamino 2-nitroso phenol. Then I had to take out the second main ingredient, which is 1-amino-naphthalene, from which I needed only 1.67 grams. The flask was mounted on the stand and the two powders were charged in it. For a solvent, I used 50 ml of 95% ethanol, which I poured in the flask. The moment it touched the solid, it quickly turned dark red, just as when the nitroso compound dissolved in water. I turned on the stirring and waited until all the solids dissolved. For this reaction to work, I have to add a catalysis, which in this case is 9 ml of hydrochloric acid. This is quite a large amount for a catalysis, but keep in mind that we also need to convert all the 1-amino-naphthalene to its hydrochloride, which will consume some of the acid. After I added it, the solution instantly started to become brighter and a precipitate formed. The precipitate could be 1-amino-naphthalene hydrochloride, since salts aren't very soluble in ethanol, but I'm not entirely sure. Then a reflux condenser was attached and the mixture heated to boiling. And here is the magic color change happening. The solution started to darken again, however this time it also looked somewhat greener. A few minutes later, things became much better because it all turned blue and also a blue-colored precipitate started to appear. Now here is an explanation why it firstly turned green and now it's blue. As you saw, the ethanolic solution of 5-diethylamino 2-nitroso phenol is red. However, NileBlue in its acid form is blue when dissolved in ethanol. So at one point we have both the starting compound and the reaction product in the solution. And if you have ever mixed dyes, you will know that when red and blue are mixed, you get green. This only meant one thing: we are successfully carrying out the reaction. The 5-diethylamino 2-nitroso phenol is reacting with 1-amino naphthalene to make NileBlue hydrochloride. The heating was continued for 4 hours to make sure everything had fully reacted. When it was done, the next thing I had to do was to remove all the ethanol alongside with the excess hydrochloric acid. This was achieved by simply distilling them. When most of the alcohol had passed over, I connected the apparatus to my vacuum pump. Water is particularly hard to distill, and I didn't want to heat my product too much, and the vacuum will help to carry out the job much more gently. An interesting thing was that the liquid in the receiver painted in very pleasant blue color. This, however, was not because I was distilling NileBlue, but because for the distillation I used the same condenser as for the reflux, and it turned out that some of the dye had stuck to its joint, and now it's dissolving during the distillation, ending up in the receiver. In the end, I was left with this solid, which looked like a mess, but hey, this is what NileBlue is typically like. I wanted a pure product though, so I decided to recrystallize it from 95% ethanol. I heated the flask and kept adding the alcohol until all the solid had dissolved. The use of a reflux condenser is mandatory in this case, otherwise it would evaporate a lot of precious ethanol, which could be used for other purposes. Anyway, the flask was left to cool down slowly overnight, and on the next day it was cooled even further with an ice and salt bath. This caused NileBlue to crystallize, so the next step was to vacuum filter it. However, the particles turned out to be even smaller than the 5-diethylamino 2-nitroso phenol, so this filtration really took forever to complete. But here is my final dried product. On camera it looks black, but that's probably because of my poor lighting. In person it is more of a green, which is actually how it's supposed to be. Let me adjust the camera a bit so you will be able to see it. It might sound unlogic that a dye called NileBlue is green colored, but a lot of the dye names come from their color as a solution and not as a solid. My final yield was 1.46 grams, which is about 36%. For me, that is pretty okay. After all, the Wikipedia page suggests yield of only 31%. Also, NileBlue is a moderately potent dye, and I need only a few milligrams of it for my demonstrations. Now I'll show you where NileBlue's name came from. I placed 400 ml beaker on my hot plate and I filled it with water. Then I added a few milligrams of NileBlue and turned on the stirring. It gradually dissolved, turning into a blue solution. NileBlue is cationic dye, because it has this nitrogen directly bound to the aromatic system, which can be protonated. In my case, I use NileBlue hydrochloride, which already has a proton attached to that nitrogen. A really interesting thing will happen if we remove it by adding a base, which in my case will be a solution of sodium hydroxide. It changed color. A simple test with pH paper shows that the pH of the solution is basic, so NileBlue is now in its basic form. It actually should be bright red. The reason that my solution is somewhat pink-purplish is probably because I didn't wait long enough for all the dye to dissolve before adding the hydroxide. And now in the solution we have both protonated and deprotonated form, which mix up to make the color. If I add acid, the solution turns blue back again. And now when all the solids are fully dissolved, I can basify the solution again, so you can see its red color in full beauty. This process can be repeated as many times as someone would like, and it will keep changing the color. This means that NileBlue could be used as a pH indicator. What do you think would happen, however, if we hydrolyze the imino group to ketone and get Nile red? Will it still be soluble in water, and will it still be pH dependent? Let me know in the comments and be sure to subscribe, because this is exactly what I will be doing in my next video. NileBlue has two more tricks in his sleeve though. These are even more spectacular than the pH color change. They are its fluorescent properties and solvatochromism. If I turn off the lights and shine UV at its water solution, nothing happens. However, things become much more different when I swap the water for an organic solvent like ethanol. NileBlue will only fluorescence in its basic form, so I had to dissolve a few pieces of sodium hydroxide in the ethanol to make it basic. Now let me turn off the lights and add some of the dye. We get a really nice pink fluorescence. On normal light the solution looks red, just as when it was in water. If I want to quickly kill the fluorescence, the only thing I need to do is just to add some hydrochloric acid to it. And the fluorescence is gone. Let me fire it up once again by adding some ethanolic solution of sodium hydroxide. Let's try this effect in a less polar solvent like ethyl acetate. Sodium hydroxide won't dissolve in it, so I have to deprotonate the NileBlue separately. To do this, I added some in a beaker and dissolved it in a minimum amount of sodium hydroxide solution in methanol. As a result, I got this super concentrated basic solution of NileBlue in methanol. The only thing left to do now is to pour some ethyl acetate in an Erlenmeyer flask and add in a few drops of the concentrate. That's what I call magic. Chemistry. We can also try a more hydroxylic solvent like ethylene glycol to see what kind of effect we will get. It's a bit more pinkish. Time to take out the big guns. I prepared some vials with all kinds of solvents I could think of to see what color would NileBlue will be in them. We've got more and less power alcohols with 2 or 3 hydroxy groups, ethanolamine, pyridine, diethyl ether and some THF. And to make it look cooler, I'm gonna add the NileBlue under UV light. Ethanol, 1 and 2-propanol gave pretty similar colors, since they got about the same polarity. The other ones, however, are clearly different. You can see that the methanol, as the most polar solvent, gave kind of a purplish color, whereas secondary and tertiary butanol goes a lot more yellowish. Furfuryl alcohol, glycol and glycerol turned out to be very purplish, but that's expected considering their structure. However, with the decrease of polarity, the color became more and more yellow, as you can see in the case of diethyl ether and THF. On normal light, the color of the solution was also different, which is a pretty good example of solvatochromism. Oh, and you think that these are all the solvents I have? Of course not! Let me bring the other ones. I've got dioxane, acetone, methylethyl ketone, ethyl acetate, acetonitrile, nitromethane, DMSO, DMF, dichloromethane, chloroform, toluene, petroleum ether, and hexane. This time, when I added the dye, I got different colors, especially in the less polar solvents like hexane and toluene. Also, as you can see, NileBlue is very poorly soluble in hexane and petroleum ether, although it's in deprotonated form, which is less polar. I will use this property in my next video, where I will have to separate NileBlue from NileRed. From all the solvents, I think the fluorescence was the most intense in the acetone. Nitromethane was kind of unique, standing out from the rest. The other ones were either yellow or orange or something in between. And that was all from me and NileBlue for this video. This synthesis was something I wanted to do for many years, and finally I am very happy that I was able not only to do it myself, but also to share it with you guys. Thank you so much for watching, and if you like this video and also wanna see me make NileRed, make sure you subscribe and hit the notifications bell on. Also, ordering reagents from Sigma doesn't come cheap, so if you'd like to support my work, you can do so by visiting my Patreon page. I would strongly appreciate it.